Again, I am back with my next lecture video, which is on code optimization. Now, code optimization can be done in various stages. We are talking about code optimization at the intermediate code level primarily. Although some of the examples will have registers in them, and that will resemble like target program code optimization, but the basic principles that we will talk about are about intermediate code optimization. Um, as you all know, that uh, the code generator is actually is the beginning of the backend of the compiler, and so this from this part towards right, everything that I will talk about, somebody talks about, is a systems program which depends on the underlying hardware system. But to the left of it, everything is pretty uh, transportable, pretty portable code, and that's called the front end. The end of the front end is the code optimization. The input to the code optimizer will be intermediate code. Output will also be intermediate code, but the code will be optimized. So when you optimize a code, the first step towards that is to find out flow graph of the entire program that is included in your three address codes. So for the flow graph, we understand what is the basic block, we find out the basic blocks, and then we draw the basic blocks, connect them with arrows to make it a graph. So what is a basic block is something that we need to understand. All of us are talking about block structured programs. So these blocks are generally synonymous with the block structured programming blocks. A block in a programming language, whatever be the language, is basically a sequence of statements which contains exactly one entry point and exactly one exit point. So for example, if I have a for loop and the for loop does not have any break or continue in it, then the for loop as a whole is entered once. Once the whole iteration is done, then we come out of that loop, and that is a block at a high level language. If we do not use gotos, breaks, continues kind of statements, then anything that is between begin and end, or opening brace and closing brace in languages like C, Python, or C, etc. Python is indentation. That is considered to be a block. Now, at a lower level, like at an intermediate code level, blocks are to be identified quite unambiguously so that we can work on that, we can operate on that. So, as I said, in a block of statements, block of three address codes, the idea is we can enter the block in the first instruction, that is the first quadruple. And in the middle of the block, there cannot be any jump, any go to, conditional or unconditional. So control can leave this block by executing the last instruction. One entry, one exit per block. So question is, how do I identify blocks in a given sequence of three address codes which contains generally go tos, etc. So we constructed by finding out the leaders of the block. What are the first statements of the block? So as I said, that a block cannot have go tos, right? So therefore, the first thing that we talk about is the first instruction of the three address code is a leader. Is the first leader means the first statement in a block. All labels corresponding to the target statements are leaders. Why? Because we'll have go to as a target. Now therefore, when you jump to that target, naturally that has to be the first instruction in a particular block, because we cannot enter the block in the middle. You have to enter into the block at the very beginning, and you have to come out of the block at the very end. These are the fundamental properties of a block. And statements following go-tos are also leaders. So a block is thus all instructions following a leader until the next leader comes. As always I do, let us take an example and illustrate this further. See, these are a series of C address code, right? Now the first instruction that is line number 1 or statement number 1 is a leader, right? Is a leader. Then go to L2. So L2 has to be a leader. Go to L3. L3 has to be a leader. Go to L4. L4 has to be a leader. Go to L1. L1 has to be a leader. So let us look at those leaders now. See, L2 is a leader. L3 is a leader. L1 is a leader. L4 is a leader, right? So all targets are leaders. In other words, statements which has a label is a leader. Why? What is the purpose of having a label? Only because you are jumping onto it. If you do not jump onto a particular statement, why do you have a label for that? So, unless or until you are duped, all label statements or labeled quadruples act as leaders. But in three-address code, labels are not specifically given. So therefore, you can only have the targets. And then what is the third rule? The statement just after the goto has to be a leader. So that gives me this to be a leader, this to be a leader, this to be a leader, this, this, even this. So these 1, 2, 3, 4, these are leaders because they are just the next statement after the goto. So how do the blocks look like now? Leader to leader. So this is the first block, as you can easily see. Leader to leader. Next block will be this one. Leader to leader. Now leader to leader. This block. Leader to leader. This block. Similarly, all these blocks. Right? How many blocks? 1, 2, 3, 4, 5, 6, 7, 8. What does the flow graph look like? In a flow graph, the blocks are connected. When will they be connected? If they come after the other by control flow. So let's look at it. So after this, automatically this comes, right? But after this block, which comes? This block, not the next block, but this block. After this, what comes? This block, not the next block. After this, what comes? The first block, right? So therefore, I have to. From B2, this is my B2. I jump to B4. From B4, I jump to B6. From B5, I jump to B7. From B7, I jump to B2. And from B3, I jump to B8. In the labels, I do not write on which condition I jump, because that may not be so important in our case, in the case of code optimization. But you remember this graph. Now comes code optimization. So once these blocks are identified, these basic blocks are connected in a flow graph, then comes the concept of code optimization. So what kind of code optimizations are done? Some code optimizations are done locally. What is meant by this locally? Locally means inside one block. And what is meant by global? Global means connecting a few blocks, we will have opportunities of optimization. In that case, that will be a global optimization. Now, there are many types of optimizations: constant folding, constant combining, strength reduction, constant propagation, common sub-expression elimination, backward copy propagation, and very similar: constant propagation, forward copy propagation, common sub-expression elimination, code motion, loop, strength reduction. This is new, for example. This is new. Induction variable elimination. This is new. Dead code elimination. That's also new. So there are some kind of optimizations that we also do locally can be done globally, and there are certain optimizations which only can be done in the context of a global optimization. We'll look at each one of them in different slides. So let us start. We may not look at all the blocks at a given point of time, but nonetheless our blocks are like this. Now we'll not show you our blocks are like this, but we will not show you the content of the block at one shot, because right now we are doing local optimization. Now point is, you see, why somebody will write R7 equal to 4 plus 1? No, nobody will write like that. But do understand that the intermediate code is not written by a human being. It is written by an algorithm. And the algorithm, however optimized it could be, it will generate many statements, many quadruples, which will have this feature. So therefore, we are taking another pass over that intermediate generated code so that we can find out the scope. So what is the scope? This x, this is the x, this quadruple is x. That's an arithmetic operation. And SRC1, first source of this operation, and the second source of this operation are literals. Then what I can do, I can simply write x is equal to, R7 is equal to 5. Right? So that is constant folding. Now constant combining, you see that the moment I write R7 is equal to 5, right? Here you see R5 equal to 2 into R4 and R6 equal to R5 into 2. So what we can do, since R4 is already fetched, what you can do here, 2 into R4 into 2, that is R4 into 4. So X and Y are in the same basic block. They have at least one literal each. Y uses destination of X. X's destination is R5, and this destination is source in Y, and none of these sources of X and Y, meaning R4 and R5, are not defined between X and Y. If they are defined between X and Y, then I cannot say that R5 is just 2 into R4. R5, if R5 is defined again, then I cannot just say that R5 equal to 2 into R4. If all these conditions are satisfied, then you can fire that rule. The rule is you combine these two statements and get R6 equal to R4 into 2. So constant folding and constant combining are about constants. Constant combining is connecting, basically using the constant for in a sequence of codes instructions in a basic block. All these local optimizations are applied on one basic block. They will not be applied on multiple basic blocks together. Third one, strength reduction. See, if R4 into R4 multiplication, as you all know, is a more strength. Strength is what? Whose strength? Operator's strength. If the operator is multiplication, it needs more time. I mean, we know that the hardware for multiplication is more complicated than the hardware for, let's say, the hardware for addition. So similarly, if I left shift R4 twice, then that is the same thing as multiplying it by 4. I just left shift it twice. I have 18. I want to multiply it by 100. I left shift 18. Add those 2 bits by 0. It is 1800. I multiply by 100. Similarly, in a binary system, multiplication by 4 by 2 is one left shift. Multiplication by 2 to the power 2 is second left shift. Multiplication by 2 to the power 3 is three left shifts. So multiplication by 2 to the power k basically involves no multiplication but a left shift operation. As you know, the left shift operation will be less costly, means its strength is less. So the moment I do this, I change this. The moment I change this, the strength is reduced. Now, in case the 2 to the power k happens to be k is equal to 1 is 2, then we can do further. If it is 2, then we do not even left shift once. We just add them together once. So that is called strength reduction. Strength of the operator is reduced, so computational time will decrease. Understand that such codes could be in a loop, and therefore if that loop runs million number of times, this saving will be there, and therefore it is not going to be a small saving. Let's go to the next. Constant propagation. It's also about constant. It's easy. First, let us have a look. See, R1 equal to 5, right? So R1, this R1 is 5. So this R1 is 5, that we know. We know that. Now R4 is R4. So instead of writing R4 is R4 plus R1, you can write R4 is equal to R4 plus 5. Using constant is primarily needed because the instruction cycle for executing an instruction with immediate address mode is simpler and less time consuming than the instruction cycle to execute a statement with register addressing. So therefore, it will be easier, less time consuming for the computer to perform arithmetic operations involving constants compared to variables. Now, similarly, here you see R1 is R1 plus R2, right? But now I know that R1 is 5. So I can write R1 is 5 and R2 is underscore x, right? So what I can do, I can write 5 plus underscore x. What did I achieve? I removed the use of a register unnecessary. Now, the moment it comes R1 plus 1, so R1 is now 5 plus underscore x. It is 5 plus underscore x plus 1. So it is become 6 plus underscore x. So I'm propagating the constant and going on getting its benefits in the same block. I'm in the same block. Similarly, R8 is R1 minus R2. What is R1? 5 plus underscore x plus 1. And what is R2 underscore x? So it basically becomes 6. Similarly, R9 is R3 plus R5. What is R5? R5 as of now is R5. That's right. But what about R3? R3 is 7 and R3 is 12 here. So the recent most definition R3 is 12. So this becomes 12 plus R5. Now R2 plus 1, I removed it, underscore x plus 1. R7 is R3 minus R1. I'm doing it underscore plus x, underscore x plus 1, minus 5, minus underscore x minus 1. This becomes minus 5. So replace the register uses with literals in a single basic block. That's the goal. And the way we can do it is at least one in an operation in one source has to be a literal, and second operation has to use the destination of the first operation. Like this destination of this operation is R1 and the source of this operation is R1. So this destination is used here, and therefore I have a chance to write R4 equal to R1 plus R5. Understandably, R1 must not have been it was 5 here. It is not redefined. For example, if it is redefined like in case of R3, then I have to take this definition. Now, in this particular lecture video, I am not telling you how to do the optimization. I am trying to tell you what are the different optimizations that exist. And of course, an advanced topic will be from a tree address code, what is the algorithm to go to these optimizations, to identify these optimizations and apply these optimizations. So first we are trying to learn what are these optimizations. And in an advanced course, we talk about how those optimizations are applied, which data structures are used for that, what algorithms are used for that. So next, let us go to common subexpression elimination. This is the simplest to understand. After all, you see R5 is R1 minus 1 and R2 is also R1 minus 1, and in between from here to here R2 has not been redefined. So I can simply say R5 equal to R2, and I need not do the same expression evaluation which I have done already, right? So this is my operation X, this is my operation Y, right? Now the source of X and Y are the same, R1 and 1, R1 and 1. The operations are the same or have the same output, and the source of this particular operation has not been defined between the X and the Y. If that is the case, then I can eliminate the common sub-expression, right? Or in fact the whole expression in this case, as it turns out to be. Now backward copy propagation. So I will propagate the copy backward. What does that mean? That means you see in this code, I get this R7, right? R7 is R6. Is R7 defined? Is R7 used here? No, R7 is not used, right? So R7 is just R6, right? It's a copy of R6. So this is the place where R6 was generated, was defined, and here R7 copies it. The question is this copy required? If I remove this line, if I remove this line as such, if I remove this line, what happens? There is no change here. No change here. Only thing, not R6, R7 should not be alive. I mean, in this local optimization, I must take care that after this block, whatever blocks to come, they are not using R7. If they are using R7, then we cannot remove this R7 equal to R6. That's very important to understand. Next comes, we are done with the local code optimizations. Now we'll be talking about global code optimizations, and naturally, I have to show you all the blocks. I have to show you all the blocks that they may have a meaning, they may not have a meaning. Don't worry about that. First, the date code. Taking the cue of the previous slide, I can say, look, R7 is defined here. Is R7 used here, used here, used here, used here? Anywhere R7 is used, R7 is not used. So what we can do, we can eliminate this code because it is a dead code. So X is an operation with no use in diffuse chain. Destination of X is an operation. X is the statement. What is the destination in that statement? R7. It is not used anywhere, right? So destination X is not live, and therefore delete X if removable, right? I mean, you can delete X only when it is not a branch statement, right? But this is too simple. Why this is too simple? See, R7, I mean, I removed R7, and I mean, why I could not remove R1 to begin with? Because R7 was using R4. So therefore, I could not remove R4. But now R7 is gone. What is the use of this R4 anymore? It's not there. But this rule that I talked about will not allow to delete R4. So you will miss the deletion of R4, right? Although as a human being, you will wonder why. I can always do that, but algorithmically, if you think about it, you can go one statement to one, but I mean one statement each, right? So when you come to R7, we acknowledge the R that R4 is already is necessary. Unless and until you take a second pass, you will not be able to know that R4 is also R4 equal to R4 plus 1. This particular code has also become utility. So next one will be constant propagation. Now this constant propagation is between blocks. Between blocks. So you see R5 is 2 and R1 is 4. But R1 is 4 here and R7 is 5. R7 R1 is used defined in this block and used in this block, right? And this Y, this is my Y, this Y is using the source of the destination. This is my X. This is my X. This is my X. And this is my Y. Now, see, R7 uses R1, right? So Y is, this one is my Y. This one is my Y. So Y uses destination of X, and destination X has only one depth at X for use depth change. That is, R1 has not been redefined again anywhere, but from which you can come to this particular block, right? And then you can change this R1 by 4. You can change this R1 by 4, right? So R1, this becomes 4 into R5. But what is R5? R5 is again 2. So R7 becomes 8 now. Similarly here, what is R3? If I look at this, I mean R3 is not here, but where is R3? R3 is, if you come like this, this come and then go back and come again. So R3 is R2 plus R1. In this journey, R2 remains 10, right? R2 is 0, not 10. This is my R2. R2 is 0 and R1 is 4. So R3 becomes R3 plus this. So this is R3. R3 becomes R2, I mean 0 plus R1, and R1 is 4. So R2 plus R3 is R2 plus 4. That's right. And then R3 becomes here. Therefore, R3 becomes R3 plus 2. Right? Similarly, R6 is R7 into R4. Right? What is R7? R7 is 8. R7 is not used anywhere, so R7 remains 8 here into R4. Right? And now, if it is 8 into R4, you know that we can then again reduce its strength by left shift by 3. Right? So as you can understand, lots of constants can be propagated among blocks, but for that a particular data structure is needed to see that before you are, I mean, when you are changing some use, the definitions that you are assuming are not redefined. So it is known as a use step chain, and it's a data structure used to apply and identify optimization techniques in intermediate code. As I said, we are trying to see what is meant by, what are the different opportunities that I can find out during optimization, but we are not trying to talk about the data structure and the algorithm to implement them. So we are trying to just figure out what kind of opportunities for code optimization exist in this in the 300 code, and we are talking about that. So next one is forward copy propagation. So copy means move. Move means one register to another. So this is a classic example of this is another example of a copy. You are copying R2 to R1. You are copying R4 to R3. Right? Now, you are writing R6 equal to R3 plus R1, right? Is R3 defined anywhere in this in its journey? No. So is R4 defined anywhere? No. So I can just do this R4. I can see R6 equal to R4 plus 1. For example, R5 equal to R3 plus R2 plus R3, and R3 I can just say R4. So if I write R5 equal to R2 plus R4 and R6 equal to R4 plus 1, you can easily see in the next round, I'll possibly say that this line is a dead and not it. So in code optimization, it's not that once I find out an optimization opportunity, I do that and stop. I find an optimization opportunity, I do that, I come back in the second person, I try to find what next. So I stop only when I find out that I cannot find any more new optimization opportunities. Next is very easy, common sub-expression evaluation. You can very easily see that it contains R4 by R7 and this contains R4 by R7. So they are, one of them can be removed, right? But only when this R4 and R7 are not defined again here. So see, R4 is not used, not defined here in this block. R4 is not defined in this block. R7 is not defined in this block. R4 is not defined in this block. Therefore, when I come here, R4 by R7 remains the same as it was. So I can simply say R8 is equal to R3, or I think R3, and if I write R10 equal to R3, then I can write R8 equal to R10. Now, why I am writing R10 equal to R3? Because if I find out that this R3 is used, right? So I cannot write R8 equal to R3, because even this R3 is changed here. So R4 by R7 value of R3 is no longer remaining. It is changed. R4 has not changed, R7 has not changed, but R3 changed. So I need to remember R3 in a different, register or address, which is R10, and that R10 I can use here. But even then, I avoided an expression evaluation. And expression evaluation could be very time consuming, very performance benefit it can give. So this is what is global common sub-expression elimination. Next comes code motion, meaning code can move. If I move the code, it is better. Why I'm moving the code? See, this is a loop, right? You can easily see that this is a loop. All of us can see that this is a loop. Now, in this loop, R5 exists. No, R5 does not exist. R4 exists. No, R4 does not exist. So doing this line repeatedly, maybe R4 and R5 will be used somewhere here later on. But keeping them in the loop and repeat and kind of executing them if over and over again, that does not make sense, no? So take it to above. Take it down. That's much better. So once you do that, it will be executed only once, and here it is being executed multiple times. So it is what we call loop invariant. What is this? It is invariant. The result of this particular statement does not change as different iterations of the loop take place. In every iteration, the value is the same. In that case, why do that? Why carry out that operation inside a loop? You carry out the operation before the loop once. That is sufficient. So that is called code motion. Loop strength reduction. This is very interesting. And you see, first of all, see T2 is equal to 4 into I. So what is this? I becomes 0, 1, 2, 3, 4, and T2 becomes 0, 4, 8, 6, 4, 8, 16, 4, 8, 12, 16. So while I increases by 1, T2 increases by 4. So if T2 increases by 4, that is what it is, then why should I multiply? I can say whatever T2 was, add 4 to that and set it as new T2. So here T2 becomes 0, 4, 8, 12, 16, 24, right? 16, 20, 24. Here also T2 becomes 0, 4, everything like that. So that is, I reduce the strength of the loop. And that's enormous. If this loop is kind of going million times, then million times this saving will occur. Enormous saving. And I think the last one is induction variable elimination. What is the induction variable? What is the loop variable? I. In this case, what is the loop variable? I. Now, how I grows? I grows like 0, 1, 2, 3, 4. How long? It goes, maybe it goes to n minus 2. It goes to n minus 2. So what will be T2's value? T2's value will be 0, 4, 8, 12, 16, 20, 24. So what will be the value of T2 at the very end? If I goes to n, T2 will go to 4n. And if I goes to n minus 2, T2 will go to 4n minus 8. That's it. So therefore, I eliminate this loop variable and instead use T2 as the loop variable. And I'm not checking for, I'm checking with T1, looks like the same. But the value of T1 is n by n minus 2 here. The value of T1 is 4n minus 8 here. Correct? So by that, I optimize the 3-address code in a global sense. I could not optimize this by looking at a single block. I have to look at all the blocks, look at multiple blocks together to have this kind of optimization. So in a global optimization, looking at a single block, the optimization opportunity will not be visible. The optimization opportunity will be visible only when you take a look at multiple blocks together and then decide on the optimization opportunity. So that's all for today. This video is all about telling you what are the scopes of optimization in 3-address code, and I guess that you have learned it well. Next, you should try. I'll give you assignments. So I'll give you many assignments like this, and I'll ask you to find out what kind of optimization opportunities exist as a human being, right? And we have already seen, it is not necessarily one optimization at a time. At a second pass, another optimization. So it's the same code. By executing 3-4 optimizations sequentially, we probably can get a much optimized code at the output. So that is the goal of this intermediate code optimization. Thank you very much for your patience. Enjoy Compiler is Fun lecture video series. And I am Shobhinan Chattobadhyay, Vice Chancellor of Technical University and then former Professor of Jadavpur University, Department of Information Technology. Will continue to upload such videos. Also, I'll upload very interesting, very lucid videos in the domain of AI and algorithms. So, watch out for those videos. Bye.